Hey, this is Mr. H, and I'm going to go ahead and walk you through how to do practice file 3-3. So as you go through here, for problem one, we're simply just drawing some vectors in to show the force of gravity on a ball in the positions shown above. So here's what you need to understand, right? In this particular problem, the force of gravity is a constant, right? The weight of that ball is always the same, and it's always acting in the downward direction. So really, once you get this vector drawn in here one time for your force of gravity or your weight, right, you're good to go because really it's going to be the same each time. So there's my Fg for my weight. And again, all I'm going to do is I'm going to put that in each time because gravity doesn't change. Again, that's a carryover from our last unit, right? Doesn't matter where we are in this trajectory. The acceleration of gravity is always 9.8 meters per second squared, and the force vector for weight is always pointing down and the same magnitude because it does not change. Now, in part two, we're going to go ahead and we're going to sort of step away from the weight here and the force, and we're going to look at velocity. So they want us to draw bold vectors to represent the velocity of the ball in the position shown above, with lighter vectors show the horizontal and vertical components for each position. So what we're going to do here is we're going to look at the components first, and then we'll put it together to find the total velocity for each position. So basically what we got going on here, folks, is we're going to take some lighter colors here. We're going to do yellow to represent the Vy. So when you first throw a ball up in the air, right, it's got its what is essentially its largest y velocity at that position. And as time goes on, that vertical velocity is going to decrease because gravity is acting the other way, accelerating it in the other direction. So the vertical velocity is going to be a little bit smaller. And then, of course, we know at the very top, our Vy is going to be 0 meters per second. Because, again, if you remember from projectiles at the very top of the path, our ball stops vertically and then returns back down the other way. And, of course, we know this is a mirror image. So if we know that the Vy going up before it reached the top was what we see here on the left, then the Vy on the other side is going to be pointing down because it's now falling, and it should be about the same magnitude here. And I did my best to make sure those were about the same. Then the same thing's going to happen for our Vy here. Again, it's going to be pointed the other direction because gravity is acting downward, accelerating it the other way, and the Vy is a little bit bigger. And then, well, at the very bottom, right before it reaches the ground, that Vy is going to be the biggest it's going to be because now it has had the most time in free fall, and it has accelerated to its largest velocity. So you should see something that looks like this. Now, if we take this, we're not totally done because we have to also consider our Vx. Now, our Vx is our horizontal velocity, and one thing we learned from last unit is that our Vx is going to be constant. So whatever I choose it to be here, I'm just going to call this my Vx. It's going to be the same in all positions because, remember, our horizontal velocity is going to be constant. Our Vx remains the same. So we see that the Vx is unchanged in all of these positions here. We'll paste that guy in. There we go, Vx. Paste that guy in. There's my Vx. So our horizontal component is unchanged. So there's our Vy and our Vx's. The last component, the last piece of this is to find what the resultant is from doing these two different velocities together. So they want us to go in a more bold color. I'm just going to go with the heavier line here and a bright pink because that's nice and bold. Okay, if you can imagine that Vy and Vx make a box here, right, we can actually take these and we can find our resultant, which would be V. Do the same thing here. We can add these up. We can find our resultant, which would be V. Here, our velocity is just horizontal. Here, if we add up our Vx and Vy, we get something that looks like this. There's our V. And again, we keep going, adding up our vectors tip to tail. We get our V. And eventually, we end up with our last velocity down here, which is our greatest velocity. So what we should see here, folks, again, is, right, over time, this vector at first, this is a longer vector. As time goes on, Right? Gravity slows the vertical velocity of the ball down, and then at the very top it's only horizontal, and then as it begins to free fall, that velocity vector gets longer and longer and longer until it is going its fastest velocity or highest velocity at the very end. Okay, so which velocity component in the previous question remains constant and why? Well, of course, we know that that is going to be our Vx because our Fx, or our horizontal forces, are zero. There is no horizontal force on our ball, so there is no acceleration horizontally. Now, which velocity component does change? Of course, that's going to be our Vy. And why? Because Fy is going to be weight, right? So we have a non-zero force acting on the ball, accelerating it towards the earth. So at first it slows it down, and then once the ball reaches the top, it then speeds it back up. But all the while, you're always accelerating towards the earth during that path. So it's important to distinguish between force and velocity vectors. Force vectors combine with other force vectors. Velocity vectors combine with other velocity vectors. Do velocity vectors combine with force vectors? That is a definite no. When we're adding vectors, we can only add vectors of the same type. Velocity and velocity go together. Acceleration and acceleration go together. Force and force go together. Displacement, displacement go together. But we can never just mix and match different vectors of different measurements. Keep that in mind. So now let's get to number 5 here. All forces on the bowling ball, weight down and support of the alley up, are shown by vectors at its center before it strikes the pin. So we're going to draw the vectors for all the forces on the ball, and then when it strikes the pin and when it after it strikes the pin. So when it's striking the pin, we definitely still have our weight pulling down. We definitely have our alley pushing up. And we know that for this one, right, our Fy is going to be Fn minus Fg, and that's going to be 0 newtons. But also, we have another force here, and this force that we have on the ball is going to be the pin pushing back on the ball. So Fx is just going to be the pin, or Fp, the force of the pin, which is going to be non-zero. So there is going to be an F net, and in this case, the F net is just going to be the force of the pin. So the pin pushes in the ball, and it causes the ball to slow down just a little bit. After the ball has knocked the pin away, we go back, we look at what forces are on the ball again, and in this case, we've got the floor pushing up, we've got the earth pulling down, and again, in this case, our force goes back to being F net is 0 newtons because the Fn and the Fg, again, cancel out. So our ball will continue on down the lane with a constant velocity, not accelerating. Okay, now, for these, we're supposed to go ahead and figure out what our F net is using this equation. So what we're going to do here is we need to isolate our horizontal and vertical forces, and then we throw it together using our F net equation. So this is pretty straightforward here, folks. In this case, our Fx is going to be 0 newtons because there is no horizontal force, and our Fy is going to be 4 newtons minus 4 newtons, which is going to be 0 newtons. So to do our F net equation, we are going to do F net equals the square root of 0 newtons squared plus 0 newtons squared, which is 0 newtons for our F net. So in this case, we see that our forces cancel. There are no horizontal forces, so our net force is 0. This object is in equilibrium. Number 2, if we look at our Fx forces here, we are going to take our 4 newtons minus our 3 newtons, and we will have 1 newton of net force to the right. In the y direction, there is no net force. So F net is going to be the square root of 1 newton squared plus 0 newton squared, which really just gives us the square root of 1 squared, which is 1 newton. So the net force here is 1 newton to the right. Okay. Next one, we've got 4 newtons up, 3 newtons to the right. So our Fx is 3 newtons. Our Fy is 4 newtons. So our F net is going to be the square root of 3 newtons squared plus 4 newtons squared, which will get us the square root of 25 newtons, which is 5 newtons. All right, so in this case we have 4 newtons to the left, and then we've got our 3 newtons down. So our Fx is going to be 4 newtons to the left. Our Fy is going to be 3 newtons down. So our F net is going to be the root of 3 newtons squared plus 4 newtons squared, which is F net is equal to the square root of 25 newtons squared, which is 5 newtons total for our F net. And again, the F net will be pointing in that direction. Is the result of doing, right, 4 newtons to the left and 3 newtons down. All right, for our next example here, the difference is that we now have 2 horizontal forces. We have 2 newtons to the left and 5 newtons to the right. So we do have to go ahead and account for that. So to find our Fx, we're going to go ahead and take those 2 forces here. And we're going to subtract them. So we have our 5 newtons to the right minus the 2 newtons to the left, which is going to give us our 3 newtons to the right. And then our y force is just going to be 4 newtons up. So the result is really just like what we had before, where we've got our 3 newtons to the right and our 4 newtons up. So we'll go ahead and do our F net is the square root of our Fy squared, so 4 newtons squared, plus our 3 newtons squared. So we're going to add 16 plus 9, so our F net is going to be the root of 25 square newtons, and that of course is going to be 5 newtons for our F net. And in this case, that force is going to be pointing because of how we have our overall horizontal force being to the right and our vertical force being up. Right, our F net is going to be essentially, right, we're looking at roughly 5 newtons up and to the right. Okay, so let's keep going here. For our next one, we have 2 newtons up, 5 newtons down, and we have 4 newtons to the left. So again, we look at our forces. Our Fx in this case is 4 newtons. Our Fy is going to be our 5 newtons down minus our 2 newtons up, which is going to be 3 newtons down. So now we need to go ahead and do our F net equation yet again here, and we're going to do F net is equal to the square root of 3 newtons squared plus 4 newtons squared, which is going to be F net is the square root of 25 square newtons, and F net is 5 newtons. So in this case, we have a total force of 5 newtons, and again, our net force is going to be pointing downward, and our net vertical force is pointed downward, and our net horizontal force is pointed to the left. So our force is going to be down and to the left, and again, that is going to be 5 newtons down and left. So now for this one here, again, we're supposed to find the magnitude of the net force here. So in this case, nothing too crazy. We've got our Fx 7 newtons to the right, and our Fy is 7 newtons up. So our F net is going to be the square root of 7 newtons squared plus 7 newtons squared. So 7 squared is 49. So F net is going to be the square root of 49 plus 49, which is 98 square newtons. So the square root of 98, which is awfully close to 100, is going to be, well, approximately 10 newtons. So in this case, we have a net force of 10 newtons that is pointing up and to the right. All right, so we'll keep going here. So for this one now, we have 10 newtons to the right, 3 newtons to the left. So we'll go ahead and isolate those horizontally. So we will take our 10 newtons and subtract our 3 newtons. And you know what? That ends up being, yet again, 7 newtons, this time to the right. And our vertical force is just 7 newtons up. So this should look pretty familiar. We have a net vertical force of 7 newtons, so we're going to take 7 newtons squared, and we're going to have a net horizontal force of also 7 newtons, so we're going to square our 7 newtons. So our F net is going to be the square root of 98 square newtons, and what we end up with, of course, is, for our F net, roughly 10 newtons, because the square root of 98 is approximately 10 yet again. So our F net is 10 newtons, and this time, right, we have a force that's pointing roughly up and right at about 10 newtons. All right, so for our next one, we now have 10 newtons down and left, and then we have our 7 newtons up and our 7 newtons to the right. So what we can do with this, if you'll recall from earlier, we can break down our 10 newtons down and left and essentially figure out that we have, in fact, 7 newtons to the left, and we also have, whoops, let's do this in a different color though. We also have approximately 7 newtons down, right? Because this 10 newtons from the last set of problems is the result of doing a vertical force of 7 newtons and a horizontal force of 7 newtons. So this 10 newtons, we'll go ahead and strike it out, right, because we have our 7 newtons left and our 7 newtons down now. So now if we isolate these forces, right, and we add them all up, we now have our Fx is going to be our 7 newtons left minus our 7 newtons right, which is equivalent to 0 newtons. And then our vertical is going to be 7 newtons up minus 7 newtons down, which is also 0 newtons. So in total, we have a net force of 0 newtons, and this object would be in equilibrium. If we look at this example here, again, we can sort of play the same game. And if we look at it, this 10 newtons down and to the left can be thought of as a vector that points 7 newtons to the left, and another vector that points 7 newtons down. So if we look, we now have 2 forces that are horizontal. So what we'll do is we'll isolate those forces, and we have our 7 newtons to the left minus our 7 newtons to the right, which is 0 horizontal forces. And then vertically, we only have our 7 newtons down. So if we do our F net equation, F net is going to be equal to the square root of 7 newtons squared plus 0 newtons squared. So our F net is going to be the square root of 49 square newtons. So our F net is just, well, 7 newtons. And that should make sense because really what happens here, right, is our horizontal forces, our 7 left and our 7 right cancel out. And what we are left with is just our 7 newtons down. There we go. So this is how you go ahead and add your vectors with free body diagrams. This is really no different than vector addition that we've done in our force table lab or vector addition that we did much earlier on in Unit 2. So we're not seeing anything really new here. The trick is just being able to draw our free body diagram and actually perform the FNet calculation. So please make sure you go back, make all necessary corrections on your 3-3 practice file, and go ahead and submit that thing to Schoology. Good luck.